What's up, everybody? Welcome to the notes for week 2, another edition of Quarantine Chemistry. I want to walk through a couple definitions with you real quick. Big purpose of this whole week was to go through this idea of inverse and direct proportionality. If you would think of a direct relationship being that as one variable goes up, the other one does as well. So kind of like your paycheck, more hours you work, the greater your pay is. That would be a direct relationship. Pay goes up as time accrued on your shift goes up. Inverse is different. Inverse means as one value increases, the other one decreases. And typically, that's going to look like a graph with a negative slope. So it's going to be at the very beginning of your XY graph. You're going to be high on the Y-axis, and it will come down as you go along the X-axis, but not just in a straight line. Typically, it's going to have some curvature to it. You should have seen those graphs in the lab that we did. So a lot of what we're going to look at today is based on that lab that y'all did, hopefully Monday and Tuesday. So inverse relationship, inverse proportionality means one value goes up, the other one goes down. Direct relationship, direct proportionality means one value goes up as the other goes up. So they go up and down together. Pressure, remember, is the force per unit area. Air pressure is caused, or gas pressure is caused by the gases hitting the container wall. Volume is the three-dimensional space that something takes up. Temperature measures the average kinetic energy of the particles in the sample. So how fast or slow those gas particles are moving around. And then mole, that's just the amount. So how many particles do we have? Remember the pressure units. Atmosphere is kilopascals and millimeters of mercury. If you look through the book, you should have seen this in the book. These are all equal to each other. So 1 atmosphere is the normal pressure that the air from sea level all the way to the edge of the stratosphere, being pulled down by gravity, exerts on a surface. That would be the same as 101.325 kilopascals. This is a different unit. And 760 millimeters of mercury, that equivalent for atmospheres comes from Evangelista Torricelli that we looked at last week. Remember, we only use Kelvin and Celsius in chemistry when we're doing any temperature recording. We don't use Fahrenheit. And anytime we need to look at a relationship or do a calculation with gases, we're going to use Kelvin. So to get your Kelvin temperature, remember, you just take your degrees Celsius and you add 273. STP, we talked about this last week as well, standard temperature and pressure. That's 0 Celsius or 273 Kelvin, and 1 atmosphere, 101.325 kPa, kilopascal, or 760 millimeters of mercury. When dealing with volumes, remember there are cubic length units like meters cubed or centimeters cubed or nanometers cubed like you had in your lab. But there's also more commercial units like liters or milliliters. You might see that when you go to Quick Stop or you run into a store, a convenience store, and you grab a liter of a drink. Important relationship to remember as we move forward if we get into some calculations next week. A milliliter and a cubic centimeter are the same volume, same amount of space. As far as the reflection on our investigation, we're going to go through the 3 scenarios you all went through. Pressure and temperature with volume and amount constant. Pressure and volume with temperature and amount constant. The last one I asked you to do was volume and temperature with pressure and amount constant. And then we're going to take a look at 2 additional scenarios. And those are temperature and volume are constant. We change the amount and see how the pressure changes. And the amount and volume, when temperature and pressure are constant, how does volume change as we pump in more gas? So we'll take a look at those here with the simulation. So the first one we want to look at, first one you looked at in the lab, you have pressure and temperature. As temperature went up, we should have seen pressure go up when volume and amount were constant. That's going to give us a direct proportional relationship. So if we look down here, the gas properties, go in, to ideal. Let's put a pump of gas in. Again, we're going to hold volume constant. So click up here. If we turn up the temperature, look at how the pressure is changing. Temperature goes up, pressure goes up. Conversely, if we drop our temperature, you can see our pressure decrease. So temperature goes up, pressure goes up. Temperature goes down, pressure goes down. That is what we would define as a directly proportional relationship. That's going to give us a graph that has a positive slope, straight line in the lab. Something like this, okay? So as your temperature is going up, you can see that your pressure is going up as well. There's a direct relationship there, directly proportional, okay? The next one we want to look at is when we have pressure and volume, temperature is constant. So we're going to change the volume and see how that affects the pressure. If we make temperature constant, we have one sample of gas in there, one pump of gas. Watch the pressure as I change the volume. Notice how I made the volume go down. I'm decreasing my volume. What's happening to my pressure? It's getting greater. What happens whenever I go and I make my volume larger? My pressure went down. So as the volume decreases, pressure goes up when temperature is constant. Volume goes down, pressure goes up when temperature is constant. That's going to give us an inversely proportional relationship. That's going to look like this. That's that negative slope curved line of a graph that I mentioned before. That's what your inverse relationships are going to look like. Graphically, as your pressure is increasing, the volume is decreasing. It's not linear, not directly. It doesn't have a constant slope. It is linear. It doesn't have a constant slope. It has this little bit of a dip to it. Okay. All right. Our third relationship is looking at how temperature and volume are directly proportional when we have one pump of gas and we've got constant pressure. So we're going to hold the pressure constant. We're going to let the temperature and the volume change. So pressure is constant. Let's heat the sample up. Notice the volume increases. Temperature's going up, volume's going up. Let's see what happens when we go in the opposite direction. Temperature goes down, volume goes down. So volume and temperature are directly proportional. They're increasing or decreasing with each other if pressure is constant. Now, we've got that same relationship. Again, temperature's going up, volume's going up. When pressure is constant, that gives us our direct graph. Now, these are the two scenarios that I want to take a look at that were not on the lab, but we're going to look at how pressure increases with amount and how volume increases with amount. All right, let's look at what happens when we have temperature held constant. We're going to look at amount and pressure. So watch the pressure gauge as we keep adding more and more gas into the container. Look at how, as we add pumps of the gas in, our pressure is going up. Let's add another one in. Pressure goes up as the amount goes up. Now, that should give us a graph that looks like this. We should have that graph. Let's see what happens if we look at how amount and volume are connected. Let's restart this. Let's put one pump of gas in there. Let's hold pressure constant and let's start adding in. Oh, we blew up the sample again. So let's move this in. We've got constant pressure. Let's see how the volume changes as we add more gas in when pressure is constant. So this is amount and volume. As the amount goes up, so does the volume. As the amount goes up, so does the volume. So that should be a direct relationship as well. So both of those relationships we just talked about, pressure and amount, volume and amount, are both directly proportional. They should have a graph that looks like graph 1. All right. Well, that's the end of our notes for this week. Please make sure that you're taking some time to really focus on what the difference is between inverse and directly proportional. Make sure that you answer the discussion question based on the lab. Then I'm going to have an optional discussion question added in as well. You don't have to participate in the second one that I'll post. Make sure that you do complete your end of week assessment and make sure that your weekly discussion summary gets done as well. Those both have to be done by Sunday at midnight. The practice test is optional, but I would go through it just to make sure you know what you're doing before you take the big test. Make sure there's nothing you're missing from your notes that would help you do well on the exam. You'll have 4 grades this week. You have your lab grade, which should be in by the time you're watching this. You'll have the discussion grade for filling out the thread based on this lab and the data we just talked about. You'll have your weekly writing assignment, which is a summary of what you've learned over the week. That's due on Sunday. And you'll have your weekly assessments. You'll have 4 grades this week. The only one that we're going to be grading on correctness or accuracy will be the assessment for this week. So everything else to that point, those other 3 assignments will be participation. But please make sure you get them done and get them done on time. Please email me if you have any questions. If there's something that you are struggling with, let me know and we'll figure out a way to clarify anything. If I have to release another video for you all, if there's something that's not clear, please shoot me some messages so that I know. You can actually add some messages right to the bottom of this in the classroom comments if you want, if there's something else you want covered in more detail. Stay healthy, be strong, improve daily. See ya.